Hi, calculus teachers. So rather than try to click my way through a demo of this live, I wanted to pre-record a video of me modeling how to sketch the antiderivative, since this is going to be an extra layer that kids have to deal with in our upcoming unit on functional analysis. So just for context, this is coming after kids have already established all of the relationships that exist between f, f prime, and f double prime, and now they're working on building those same connections back to big F, the antiderivative function. So one of the more rigorous skills that students are going to need to be equipped to deal with is how to sketch an antiderivative given a graph of the original function of f. So this is an example from our unit packet that I wanted to walk you through. So in these settings, you're going to be given an initial condition to kind of anchor you on your graph. And in this example, that's at -1, 12. So I'm going to just plot a point, I'm going to try to, sorry, at that location. Forgive me, I'm using my finger here on my snipping tool. So if I'm off, it's going to lead to some problems. So just pretend that that's at -1, 12 for me, and it'll be easier when I sketch the actual curve in. So I tried to get as close as I could. So what you're going to want to distinguish for your kids during this time is how certain behaviors on the original function actually impact behavior on the antiderivative graph. So what I'll do with my kids oftentimes is highlight a certain portion of the graph and annotate that completely, and then build in the connections that exist for the antiderivative and sketch one little chunk at a time. So for example, this highlighted piece that I just drew our attention to, I would say for that portion of the graph, two things are significant about f of x. First of all, f of x is positive because I'm anchored above the x-axis, and additionally, f of x is decreasing on that highlighted window. And if you can get kids to just verbally describe what's happening on that highlighted piece, then the extra piece is to come in and make conclusions about what those indicators tell us about big F. So if f of x is positive, what I know then is that the antiderivative is increasing. Similarly, if f of x is decreasing, then the antiderivative, the function that came before, has to be concave down. So what I want to do on this stretch of graph is draw something that's increasing and concave down and anchored at that initial point. So maybe something like that. And then we're going to move on to the next portion of graph. So we're going to kind of cut that analysis off and switch gears to the next significant features of our graph that exist on the next window. So from here, we'll ask kids to identify certain characteristics here. We'll say f of x is still positive because I'm anchored above the x-axis, but now f of x has switched direction and is an increasing function. So we'll popcorn around the room and say, what does that tell us about big F? There should not be any surprises on the first part. If f of x is positive, big F is increasing. And if f of x is increasing, big F is now concave up. So for this next stretch of graph, I need to remain increasing, but this time concave up is the characteristic. Sorry, I had to extend my line a little bit, and I'm definitely going to go off the graph here because I can see just by thinking about this entire graph's positive, so I need to maintain increasing behavior all the way through to the end of the domain. And I'm chunking again, so we're ready for the next piece. I see the next highlighted portion coming into play. We've got an original curve. I'll try and keep my colors the same. An original curve that is still positive and an original curve that is decreasing again, which means that on my new red antiderivative, I'm going to have big F increasing and big F back to concave down. So I'm going to try my best to draw something on this next window that's still an increasing curve, but whose concavity is now downward. Sorry, not the prettiest, and I'm trying not to decrease there at the end, so I'll have to scroll up here in a minute to really capture the rest of that behavior. And you know that if you're doing this with like an expo, this is not going to be as jagged or disgusting as mine is. So I'm really sorry for that. Last piece, that last little stretch of curve, I've got again a function that's positive and a function that's decreasing, which leads to an antiderivative that's increasing and an antiderivative that's concave down. So increasing and what did I do, you guys? Oh, hold on. I knew something was off here when I went to sketch this. So this last piece is an increasing curve, which means that my antiderivative is not concave down. My bad. It's actually concave up. So I've got my last little stretch of graph increasing and concave up. And I would really try to like clean this up with kids, like concave down, concave up, concave down, concave up. And you can confirm with them that these special points where the concavity changes, we know what those are called. Those are my points of inflection that are occurring on my antiderivative graph, and those are great. I can confirm those to be the inflection points by looking at the original curve, since that's where the change in direction occurs. So this is just a perfect opportunity to formulate lots of great discussion with your students while really pushing the rigor in your class and building their graphical analysis skills and their curve sketching skills. Okay, so I'm going to turn this off and go back to the live video, so hopefully I can address any questions or comments or take any pieces of advice that you might have about how to make something like this go smoother.